Okay, so we have our Hamiltonian for the helium atom, and the question is, and I'd like you actually to pause the video and take a minute to think about this, how could we use our approximation methods that we discussed in the last chapter to address this problem, right? So we have the variational theory, and the question here would be, what would be a good trial function? And for perturbation theory, what would we consider our basic system, or our ideal system, the one that we know the answer to, and what would be the perturbation? So go ahead and pause the video and take a minute and think about that. I'll wait for a second. Okay, so hopefully you had a chance to pause, think about it. Hopefully maybe you got out a piece of paper and wrote down some ideas. And so we'll start with perturbation theory. So perturbation theory, if we're looking at the helium atom, we know that we have two for each electron by itself. If we ignore the electron-electron repulsion, we can solve those problems. So if we have this 1/2 del 1 squared minus 2 over R1, right? All these involve just electron 1. And we'll have another term that's very similar for electron 2. That should be a 2. And these are terms that only involve electron 2. We can solve each of those separately. They essentially are like the hydrogen atom, where we have a charge 2 on the nucleus instead of charge 1, but that doesn't fundamentally change the problem. You get the same solutions. What we have extra is this term that depends on the electron repulsion. And this is what we are going to treat as our perturbation. All right, and so our ideal Hamiltonian, we could say, is H is the Hamiltonian of basically the hydrogen Hamiltonian for electron 1 plus the hydrogen Hamiltonian for electron 2, and then our 1 over R12, that'll be our H1. Right, so this combined is like our H0 that's in our perturbation theory. Okay, so if we're looking at, say, the 1s orbital, what are our ideal wave functions, or our zero order wave functions? So say for a 1s orbital, we could do this for other orbitals as well, but we'll just think about the ground state. Our zero order wave functions are just going to be a product, right? So if we add Hamiltonians, we multiply wave functions, kind of like we saw with the 3D particle in a box. We'll have a product of a 1s orbital for electron 1, and let me keep my notation consistent with my notes here, and a 1s orbital for electron 2. All right, and so then our first order energy correction for this would be an integral. This would actually be a triple integral, but I'm just going to write it in shorthand here. We'll have psi star 1s1, psi star 1s2, our perturbation, R1 over R12, and then we have psi 1s1, psi 1s2, d tau. All right, ran out of space there. That's just one long integral. Okay, so we can solve this. This is something that goes in the book. It goes through the example of doing this. And what we'll do is we'll solve this in terms of z, where z is the charge on the nucleus. So if we solve this, we get E equals minus z squared plus 5/8 z, and that's equal to negative 11 over 4 Hartrees, or negative 2.750 Hartrees. Now the measured experimental value of the energy of a helium 1s orbital, and we can find this by ionizing the helium. You take off one of the electrons, that tells you how much energy it had. We set 0 as the the electrons free from the nucleus. The experimental value is negative 2.9033 Hartrees. So we get something that's about a 5% error, which for this simple sort of approximation isn't too bad, but we need to do better than that. So this approach is not going to work. What we can do is use. So we just did first order perturbation theory, and as we talked about briefly, we can go to higher orders, and we can use the same approach with higher order perturbation theory. If we do multiple order perturbation theory, it takes a lot more work, but we can get a much better answer. We get minus 2.9037 Hartree. A lot closer, but a lot more work. All right, in the next video, we'll start looking at variational theory approaches to finding the energy of a helium atom.